Welcome back, class. So today we are going to wrap up our discussions of Chapter 5 and talk about another type of reaction, and these are what are known as oxidation-reduction or redox reactions. Now, unlike the acid-base precipitation and gas evolution reactions that we've been talking about, these reactions will not always occur in aqueous solution. Some of them will occur in the solid state, etc. So these are not technically always aqueous chemistry like what we've been seeing. We're just going to sort of touch the surface of redox chemistry. Much like acid-base chemistry, we will discuss this in much more detail in a chapter in the second semester if you take Chem 2. But for now, let's talk about the basics of oxidation-reduction chemistry. Now, one of the reasons we look at them at this point is that they are a really important type of reaction because they occur in lots of different places all around us. So we can list just a few examples of where we see redox chemistry and may not even realize it. We have, burning, right? Or what we called combustion. We have corrosion of metals, right? What you might know as rusting as an example when we think about it with iron, but lots of metals corrode, and these are also types of redox chemistry. We have energy production in the body. Consumption of glucose, of the conversion of glucose into energy in the human body, is a redox reaction. Photosynthesis in plants, another example of a really, really important redox reaction. Bleaching, whether that's hair bleaching or laundry bleaching, another place where we see redox chemistry. So, bottom line is, there's a lot of redox chemistry that happens all around us, and so it's useful to understand sort of the basics of what's going on. Now, when we have redox, as the name implies, we have two important concepts that are going on here. We have an oxidation and we have a reduction. So the oxidation first, right? Oxidation is simply the loss of electrons, while reduction is the gain of electrons. Now, this does not necessarily indicate the formation of ions, right? We do not have to have the complete transfer of electrons in the sense of forming an ion for this to occur. And sometimes what this involves the movement of electrons involved in covalent bonding that we discussed, the sharing of electrons. So we won't always think about redox in the sense of formation actual ions. It can occur in covalent compounds as well, or with compounds with covalent bonds as well. Now, sometimes these terms are tricky to remember. So one technique that has been used is these mnemonics. So the most common mnemonic here is to use the term oil rig, right, where oxidation is loss, reduction is gain. So we have oxidation and reduction. Now, these two processes must occur simultaneously or at the same time. In other words, we don't have the loss and then the gain. It happens all at once. Right? They're happening at the same time. Now, one of the ways that we keep track of this is with the use of what are called oxidation states or oxidation numbers. And what these are sort of fake charges, right? So these are the charge that an element would have if all shared electrons were given to the element with the strongest attraction. So the idea is, this concept is most important when we talk about molecular compounds where the electrons are shared, and the idea is that we assign the electrons to the element in the bond that has the strongest attraction. And by assigning these electrons, then we set up the situation where some of the elements in that compound will have a negative oxidation state, meaning they have a higher attraction for the electrons, and others will have a positive oxidation state, a weaker attraction for the electrons. In this way, it gives us a way to sort of keep track of where the electrons are at. Now, a couple of other terms that we want to illustrate here are, first of all, we have oxidizing agent and reducing agent. Now, again, I will apologize in advance, right? These terms are often confusing, especially with oxidation and reduction. But with a little practice, we can learn to differentiate them. So the oxidizing agent is the reactant that causes oxidation in another reactant. So the oxidizing agent causes something else to be oxidized, and that means it is reduced. So the oxidizing agent is always reduced. Now the reducing agent is just the opposite, right? Reducing agent is the reactant that causes reduction in another reactant. And of course, it itself is going to be oxidized. So by causing something else to undergo reduction by being oxidized. Okay, so we have these terms, right? These four, right, are the ones that, we will have to sort of assign, right? We're going to assign oxidation and reduction. We're going to assign the oxidizing agent and the reducing agent. And the oxidation states we use to do this. So let's look at this example that I have here and just kind of briefly run through it, and then we'll do some practice. So if we look at this reaction here between magnesium and oxygen to form magnesium oxide. So you can see here that the magnesium has an oxidation state of 0 here. The oxygen has an oxidation state of 0. Within the compound magnesium oxide, magnesium has a 2+ oxidation state and oxygen has a 2- oxidation state. So what this means is that over the course of the reaction, the magnesium has been oxidized, right? It has lost electrons. It has taken on a more positive oxidation state, right? Remember, positive charges indicate the loss of negative, right? Or the loss of electrons. Whereas the oxygen has taken on electrons and the oxidation state of the oxygen has gotten more negative, right? Indicating the gain of electrons. And so magnesium is oxidized, oxygen is reduced, so that means the material that is reduced is the oxidizing agent. So O2, right, becomes the oxidizing agent, and solid magnesium, which was oxidized, becomes the reducing agent. Now, one distinction I'll make here as we go through it, and I'll remind you, is that the agents, first of all, are always reactants, and they will be the entire reactant. So while individual elements undergo oxidation and reduction, when we talk about the agents, we talk about the entire reactant that is causing it. So, we say O2 or magnesium solid or whatever the compound may be that contains the element that's acting as the agent. Okay, so let's look at a couple things. First of all, I told you these oxidation states, but how did we get there? So let's look at how we assign oxidation states. So it's pretty straightforward. We have a set of rules. So you do have to know these rules, right? So you will need to know the rules. So the first thing is any free element is assigned to 0. So we saw in that reaction that magnesium metal and O2 gas were assigned oxidation states of 0, right? That's because they're in their elemental form. If we have a free monatomic ion, its oxidation state is equal to its charge. So for example, if we just showed in the equation something like Fe2 plus ions, right? Then the oxidation state would be 2 plus. Now, this one is important here. Well, maybe one of the most important ones. The sum of the oxidation states of all the atoms in a compound is 0, right? So if it's a neutral compound, all of the oxidation states must add up to 0. If we are dealing with a polyatomic ion, the sum of the oxidation states of all the atoms within that polyatomic must add up to the charge on the ion. Now, those are the general rules. Now we have some specific rules for specific elements or groups of elements. So first of all, group 1 metals, right? These are your alkaline metals. They will always have positive 1 oxidation states when they're in a compound. Group 2 metals, alkaline earth, will always have positive 2 in a compound. Now, other metals, we don't have specific oxidation states that we assign to them because they often take on other oxidation states or multiple oxidation states. So we'll be able to assign them by difference, we'll see, using rules 3 and 4. Now, there's also groups of nonmetals that we can assign oxidations to according to this table. And this table is in order of importance. So it's a ranking. So if there's a conflict, right, the one highest in the table is going to take precedence. So the highest priority is fluorine, and fluorine in the concept will always be -1. Hydrogen hydrogen will almost always be positive 1 in a compound. Oxygen has the next highest priority and takes on a -2 oxidation state, and it will always be -2. One exception that you might run into is in peroxides. It's going to be a -1. Now, you notice we haven't given rules for all of them. Well, now we have sort of groups of rules where the other group 7 elements, so the other halogens, like to take on a -1, but won't always. Other group 6 elements, besides oxygen, like to take on a -2, but will not always. And other group 5 elements, like nitrogen, or the group 5 elements, will take on a -3, but not always, right? For example, if I have both, say, nitrogen and, let's say both sulfur and oxygen in a compound, they both can't be negative, right? So the oxygen has priority, it will get the negative oxidation state, and sulfur will take on whatever oxidation state's necessary to satisfy, again, rule 3 and 4. But the sum of the oxidation states have to be 0 or some charge if it's a polyatomic ion. Okay, so let's put these rules into play. So if we look at our first example, chromium, right? Chromium is a free element, so it's going to have an oxidation state of 0. Chromium 3+, right? This is considered a monatomic ion, right? Oxidation state is going to be equal to its charge, 3+. So here we have a compound, right? Carbon tetrachloride, right? So one way that I like to show this out is just simply to draw the elements. So C, Cl, 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 Cl. And then assign what we know. So we have a rule that says group 7 elements like to be -1, right? If there's nothing with higher priority, right? And there's not. So all these are going to be -1, -1, -1. And we know that the sum of the oxidation states have to add up to 0 because it's a neutral compound. So carbon, which of course we don't have a rule for, must take on, in this case, a +4 oxidation state to make this add up to 0. So in this compound, the chlorine is -1, the carbon is +4. SrBr2, so we have Sr, Br, Br. Again, we have rules for everything here, right? Sr is a group 2 metal, so it's going to be a +2. Br is a group 7, so it's a -1, and of course, all works out very nicely to add up to 0. How about SO3? So again, everything has to add up to 0. We have oxygen has the highest priority, right? And it's going to be a -2, -2, -2. So to make this work, sulfur has to be a +6. And so sulfur takes on a +6 oxidation state, while oxygen is a -2. Okay, NO3-, right? So it's the polyatomic ion nitrate. So we have NOOO. Now, different, this is a polyatomic ion, so the charges here have to add up to the charge, not to 0. So -1 in this case. So oxygen again has priority. So -2, -2, -2. So we got -6. But nitrogen won't be +6 because that would give you 0. It's only going to be +5 to make it add up to -1. So we look at Fe2O3. Okay. So we have Fe, Fe, O, O, O. So again, these have to add up to 0. Now, oxygen, we have a rule for. It's going to be -2, -2. So it's -6. So that means the two iron atoms, which will have the same charge, right, have to split the difference. So we need a +6, right, to make this add up to 0. So each of these would be +3. Within this compound. N2, right? N2, this is an element, so it's going to have an oxidation state of 0. Okay, so here we get the idea of using the rules, right? So what we want to do with this is then take these rules and apply them to reactions, right? We want to analyze redox reactions. So let's take a couple of sample reactions. So here we have reaction between lithium and chlorine gas to form lithium chloride. So the first thing is we assign the oxidation states. So lithium being an element, given 0. Cl2, again, an elemental form, 0. So within the compound, we know lithium is a group 1 metal, so it's going to take on a +1, and that means chlorine is going to be a -1, which, again, that's what the rule tells us. So, what's oxidized? What's reduced? So, if we look at the changes, lithium goes from a 0 to a +1. Right? Well, that oxidation state getting more positive, right? That's what we're looking for. The changes from reactant to product side is an indication of a loss of electrons or an oxidation. Now chlorine goes from having a 0 to a -1. So this reduction in oxidation state indicates that organic electrons are undergoing a reduction, right? Notice the reduction in oxidation state corresponds to a reduction. So if we answer our questions, the element that is oxidized, right, that's lithium. The element that's reduced, that's Cl. Now the oxidizing agent, right? So the oxidizing agent causes oxidation, it's reduced. So we saw that chlorine is the element that's undergoing reduction, so the reactant that contains the chlorine is Cl2 gas, right? That's the oxidizing agent. The reducing agent contains the element being oxidized, so that would be the lithium. Okay, so let's try one more. So here we have aluminum. So elemental form, oxidation state of 0. Sn2+, right? This is a monatomic ion. Its oxidation state is equal to the charge, 2+. We have Al3+. So again, monatomic ion, in this case with a 3+, but a tin metal, elemental, it's going to be 0. So if we look at the changes, we see that aluminum goes from 0 to +3, so indicating a more positive or a loss of electrons or an oxidation, whereas the tin ions go from +2 to 0, right, indicating that it got smaller, got reduced, or gained electrons, underwent reduction. So the element that is oxidized is aluminum. The element that is reduced is the tin 2+ ions. So now the oxidizing agent, right, contains what is being reduced. So in this case, it's simply just going to be the Sn2+ ions are the oxidizing agent, and the reactant that contains the element undergoing oxidation is going to be the aluminum metal. That is my reducing agent. Okay, so now we sort of get the idea. So we can analyze redox reactions, but take a moment here and just sort of summarize some of the basic patterns we see in redox that might help us sort of more quickly identify them, whether they're redox or not redox. So really, we've seen three sort of families of redox reactions. The first one, which we saw earlier, are combustion. And so remember, this is a reaction of a carbon, so we'll just say, well, mostly the ones we're dealing with are hydrocarbons, but basically reaction of an organic compound with oxygen to form water and typically carbon dioxide. So these are, our burning combustion. A second class is the reaction of a metal plus a non-metal. And that non-metal might be something like O2, could be Cl2, be Br2, right? Could be various non-metals, oxygen being a very common one, but also other non-metals as we saw, like chlorine. So this is an example of that one. And the third basic type that we'll see quite often is the reaction of a metal plus metal ions. And this here is an example of that. So we got combustion reactions, which we've looked at before. We have a metal plus a non-metal. And this typically, if you think about it, will give an ionic compound. And then metal plus metal ions. So in the last section, I want to focus on this type of reaction. I want to look at how we can sort of look at more detail on these reactions between metal and metal ions. Now to do this, we're going to look at what's called the activity series of metals. And essentially what this does is it just ranks metals in how easily they undergo oxidation. So metals, as we learned when we looked at the periodic table, like to form positive charges, right? That's how they become stabilized, become like a noble gas, etc. Right? So metals like to form positive charges. That's what they will do. But some like to do it more than others. So metals listed at the top of this table are the most easily oxidized and have the strongest tendency to lose electrons. As we get to metals at the bottom of the table, these are hard to oxidize and have a low tendency to lose electrons. And so one way that we might think about them is, when we talk about metals up here, these, as we rank, the metal let's look at this. The metal ions are the stable form, meaning this oxidation reaction is favored. Now it's more strongly favored up here, and it gets gradually less favored as you go down. When you start getting into metals at the bottom here, the metal is favored, meaning these materials would prefer to exist as the actual metal as opposed to the metal ions. Right? Okay. So let's first just look at some simple ranking So which metal is most easily oxidized? Well, they're ranked from top to bottom, so we just simply look at it and we see calcium, right? Very easy to oxidize. And your group 2 is going to be the easiest. Then we see iron, right? It's easier. Silver is way down here at the bottom. Very hard to oxidize, right? Doesn't corrode, right? So when we think about these being oxidized, right, this is also, we can reference what we know about metals and how they oxidize or how they corrode, right? We may not know exactly what calcium does, but we know it's highly reactive, right? It's one of those highly reactive metals. Iron, we've seen it rust. And maybe silver, right? We know silver, gold, right? These are metals that are essentially unreactive, right? Now, let's look at it from the reverse perspective. Let's look at the ion form and say which of these ions is most easily reduced. So, in other words, which of these ions is going to most likely want to go back and be at the metal? Well, this is going to sort of go in reverse, right? Since metal's at the bottom, right, the metal is the more stable form, and so the ions are more likely to be reduced back to the metal if you're at the bottom of the table. So copper 2 plus is going to be the most easily reduced, and then they're going to get harder to reduce as you go up, of course. So we get to chromium, right? And then, of course, something like potassium, right, an alkali metal, is going to be, almost impossible to reduce, right? It would much, much rather exist in the oxidized, in the ion form, right? Alkali metals are the most reactive metals on the periodic table. Okay, so we want to understand the basic pattern of here. Now, what about when we combine these together? So, on the previous slide, we had the reaction between aluminum metal and it was tin ions. Right? And we showed that reaction, but how do we know for sure that this reaction would occur? Well, the idea is that when we're looking at these, the metal always has to be higher in the periodic table, right? So we need a metal that's going to be more easily oxidized to give its electron to ions that are going to be more easily to reduce, right? That are going to be lower in the table. And so if we find aluminum here, right, up here, we find tin down here, right, we can see that electrons would easily flow from aluminum down to tin. Right? Going to be easy to lose up here, harder to lose, that means easier to gain down here. So this reaction would indeed happen. Right? It would be what we call spontaneous. And so generally speaking, electrons will flow down the table. So if we're talking about reacting a metal and a metal ion, the metal always has to be higher in the table than the ions that we're trying to give the electrons to. So let's look at the next one. We got iron, metal, and magnesium 2 plus ions. So we got iron here. We got magnesium ions up here. Well, in order for this to happen, the electrons would have to flow this way, right? That is not going to happen, right? So is this reaction spontaneous? No, right? This reaction will not occur. Electrons will not flow up. Now, what we could say, though, is that they will flow, it will occur in reverse. So let me just move that down. If I were to take magnesium metal and put it in a solution with iron ions, the reaction would go this way spontaneously, right? So if we look at a reaction and it's non-spontaneous, that means the reverse reaction will be spontaneous, right? Because we can see magnesium metal would give its electrons to iron ions because iron is below it in the table. So let's look at the next one. Oops. So here, again, we have iron metal. And we're trying to give these electrons to lead ions here. So, yes, the ion is below, so iron will indeed give its electrons to lead, and so we could say, yes, this is spontaneous, and this reaction would occur. And, another way to sort of look at this is that the metal that is formed should be more stable, right? In other words, lower in the table than the metal we started out with. So we started out with iron, we formed lead, right? That's going to be fine. Up here, we started with iron, formed magnesium, right? We are not going to form a metal that is more easily to oxidize, right? So that's another way to sort of look at these and see what's going on. Okay, so that brings to a close what I want to talk about redox reactions at this point. So we want to be able to understand oxidation states, be able to recognize certain types of redox reactions, and analyze them, signing oxidation states, identifying what's oxidized, what's reduced, oxidizing agents, reducing agents, and then work with the activity series to predict which metals are more easy to oxidize, easy to reduce, the ions easy to reduce, if reactions will occur. And, of course, this table, you do not have to memorize it, right? You will be given the series on a test if you need to use it as a reference, right? You don't need to memorize the order of this table for sure. All right, so remember to watch, if you haven't already done so, the supplemental videos that I've included that talk about some of these ideas of acid-base, redox, that will reiterate some of the ideas that we talked about and expand upon those ideas as well. Next time I see you, we'll be talking about Chapter 6.